Hello, my name is Steve Mann. Welcome to my course on wearables and wear tech, wearable technologies, intelligent imaging and sensing and meta-sensing. I'm at home now at my home studio. I live with my wife and 2 children upstairs, and downstairs is sort of my research lab, studio, whatever it is, here in Toronto. And I want to teach about wearable computing and wearables, which is an exciting new area that we see lots of technologies like this. I'll talk about the invention of the smartwatch, eyeglasses, brain sensing, wearables and mental health. This is one of our products. It's called the Muse, the brain sensing headband. And what it does, this is it right here. What it does is you wear this thing, and people don't normally wear it outside in day-to-day life. They use it for 5 minutes every morning to strengthen the mind. It's like a way to train your brain. We've gone through several iterations of it. This is the newer version here, the new Muse, and then we've got an even newer version, and then we got the Muse S Sleep Band, and we also provide the technology to other manufacturers. So, for example, we provided the technology that's made in these eyeglasses. And Interaxon is a company, a wearables company that was founded right here in my home live-work studio space. With my students and I, together with Ariel Garten and others, and that's an example of a wear tech company. Wear tech, here's another example, the Blueberry eyeglass, blueberryx.com, and so the Blueberry eyeglass, we have the brain sensing near-infrared spectroscopy here. It senses mental health and well-being, and there's a little indicator here on the head-up display that shows if you're dragging, it will show up blue if you're dragging, not enough oxygen to the brain, hypoxic. If you're rushing or being rushed, it'll show up red or magenta or shades of orange or yellow. And if you're playing on tempo, so to speak, a nice happy way in between those extremes, it'll show up green. And so I'm using kind of that whiplash metaphor for dragging or rushing or somewhere in the middle of those two extremes. So wearables, this is something that I've been doing since my early childhood. I've been fascinated by technologies that become part of us, that extend, technologies that function as a natural extension of the human mind and body. And so, for example, one of my childhood hobbies was photographing electromagnetic radio waves. I used to turn television receivers into oscilloscopes, oscillograph device to plot graphs. And when I was in my childhood, my dad got me this oscillograph, cathode ray oscillograph, which is a device that plots graphs on an electron tube, a very simple device. And inside there is this thing called a cathode ray tube. It's an electron tube, and on the screen of the tube there's a phosphor and the electron beam. The electron beam that you see here directs electrons to there's a particle accelerator here, directs electrons to the phosphor screen and creates a pattern on the screen. And of course, this is how I made my early wearables, as I put miniature cathode ray tubes in eyeglasses and things like that. So one of the things that I used to do is photograph electromagnetic radio waves. So I got this oscilloscope, and interestingly enough, when my father got that for me, someone was throwing it away, of course. It was broken. It was no good. At the time, the time base wasn't working, so the dot would only go up and down. There's no time base to carry the dot from left to right. An oscillograph, or now called oscilloscope, is a device that plots graphs basically using electricity, using the electron beam, which can be deflected quickly. An oscilloscope, or oscillograph, is a device that plots graphs. So these devices plot basically a graph, an XY plot, or a plot as a function of a time base of whatever's coming in. So the idea of the fundamental sort of simple device the oscilloscope is a graph plotting machine. And let's open it up and take a look inside. Oscilloscopes are widely used in electrical engineering. What's really nice about this oscilloscope is you can see everything in here. There's a cathode ray tube, the electron beam. You can see the electron beam forms up here. It's a transparent cathode ray tube, so you can see completely inside it. There's the vertical deflection plates, the horizontal deflection plates. The vertical deflection plates come first because we want them to be more sensitive, so that we're sensitive to the input signal, because the horizontal is often the time base, and so it can be a little less sensitive. And then these are the vacuum tubes. They're like light bulbs. They, inside each tube, there's a filament or heater. And the beautiful thing is there's this high voltage rectifier here, and you can see you have the filament here, and the plate is just some distance away from the filament. So you can see in there, it's very simple to understand. It's just a light bulb with a filament, and the electrons go towards the plate, so it's a one-way valve for electricity. So it's a very, very simple device to understand, and I grew up sort of understanding the world this way in a very, very simple fashion, and so that we could see and understand what was happening in the world around us. Connected to the oscilloscope was a police radar. What I discovered is that when I had a police radar that I was trying to fix, and police radar has an antenna portion like this, and it's connected to this control unit with the display in it. It has the Nixie tubes in it, and it even came with some tuning forks to relate the Doppler speed to velocity, the Doppler pitch to velocity. So that tuning fork is 35 miles per hour. And this tuning fork is 65 miles per hour in the X-band, radar X-band. And so what we have is we have a relationship between speed and the Doppler shift in frequency. So what I did, because I wanted to see the waveform on the screen, even though the dot would only go up and down on the oscilloscope, I wanted to see it. I was kind of impatient, wanted to see it right away. So we had around the house, we in our childhood we had Rollerskates, and that was a common thing back in the 1970s, Rollerskates. And so what we used to do is we used to put them on wooden boards so we could roll down the sidewalk. We called it sidewalk surfing, what people now call skateboarding. And so I had these around, so we put them, they roll like this, and we put them on a piece of wood so that we could, so that I could put the oscilloscope on there, and I would slide the oscilloscope back and forth like this so that I could see the waveform upon it. And what I discovered, I'll turn the lights down here so we can see it. And what happens is, as I moved this oscilloscope back and forth, the dot went up and down on the screen as the waveform was there from the Doppler radar, and I could see that on the screen. The dot went up and down as I move it back and forth. As I move it slowly, the dot goes up and down slowly. And as I move it quickly, the dot goes up and down quickly. So what we have is a function of space rather than a function of time. The police radar here has In it, it has these Nixie tubes, these light bulbs. Each of the light bulbs has a separate filament, one for each digit. And see, I'm moving at 2 miles an hour there. You can see the numeral 2 on there. That's 1 mile an hour, a little slower. And so you can hear the Doppler shift, that's 3 miles an hour. You can hear the Doppler shift there. It's about 1 mile an hour. It's 1 mile an hour. 3 miles an hour. 5 miles an hour. 3 miles an hour. 4 miles an hour. And so on as I speed up. So the amount of Doppler shift is thus visible in this trace here. As I move it faster, the trace bobs up and down faster, and as I move it slower, the trace goes up and down slower. Okay, so let's try some long exposure photography. I'm just going to right now change the shutter speed here to quarter of a second, so you can see there's a little bit of motion blur here. Take a light bulb. So now I turn down the lights. Now they move that oscillograph. You can see the pattern on it on the screen there. Pretty good there, you can see that. As I move it slowly, you can see the trace goes up and down slowly, and as I move it a little faster, it goes up and down faster, and thus it traces out the path. You can see this electromagnetic radio wave as a function of space rather than a function of time. And I called this the sequential wave imprinting machine, SWIM, because it shows this waveform sequentially as a function of space, unlike a traditional oscilloscope. And this is kind of what led us to this notion of augmented reality or X-reality. XR is extended reality, to extend the human senses and allow us to see, for example, see electromagnetic radio waves, see sound waves, and see other phenomena. So I'm actually seeing that electromagnetic radio wave as I move this back and forth in front of the Doppler radar, because it's causing the Doppler shift that I'm observing. So this was an interesting discovery in 1974 that I called sitting waves, in contrast to standing waves. As I move it back and forth, the dot goes up and down. If I move it faster, the dot goes up and down faster. And if I move it slower, the dot goes up and down slower. And so what it does is it traces out the waveform of that radar as a function of space rather than time. So this is one of the things that I was fascinated with. This was a discovery that I could see and understand electromagnetic radio waves as an overlay on top of the reality in which we're now sitting. And so here's a modern replica of that same thing. I've got this row of lights that provides that same effect here. I have here a smartphone, homemade smartphone, and I can see the electromagnetic radio waves coming from it as I move this sequential wave and printing machine back and forth in front of the smartphone. And so you can see those waves are there, and if I place a piece of wood in front of the smartphone, you can see the waves are weaker going through the wood when they're not going through the wood. Notice the difference in amplitude when we're going through the wood and not going through the wood. There's without it, and here's with the wood present. And if I take a brick, it'll block even more of the waves. It's even weaker going through the brick than it is through the wood. And if I take the wood plus the brick, put them both in front of it, it's even weaker now than it was before. Now, an interesting question, if I go through my hand, do you think that my hand, human flesh, will block more or less radio waves than the brick or the wood or the combination of the wood and the brick, or somewhere in between, or more or less? I'll take a minute and think about that. Now here's the answer. If I put my hand in front of the smartphone, it almost completely blocks the electromagnetic radio waves. We hardly see anything coming through here, versus if I don't have my hand. In fact, if I put one finger, here is with no blockage, put one finger over it, 2 fingers, 3 fingers, 4 fingers, versus not blocking it. So you can see that the electromagnetic radio wave is blocked by putting the fingers over the smartphone. And so now we've learned a lot there about electromagnetic radio waves. With this augmented reality, we're able to see radio waves and see sound waves and see other waves, and we can see otherwise invisible or hidden things. And that's what the eyeglasses do. It allows you to see these waves. You can see your own brain waves. You can see your own electrocardiogram. I spent a lot of my childhood photographing radio waves, sound waves, and also looking at my own electrocardiogram while I was jogging or running, looking at my own electroencephalogram, my own brain waves, doing biofeedback, a lot of these wearables. So a lot of these technologies that we will be talking about in this course are different forms of devices like this, like these ITAP devices that help us see and understand otherwise invisible phenomenon. And even the smartwatch, something that I created the world's first smartwatch in 1998. It was on the cover of Linux Journal in 2000. And even smartwatches are one form of wearable, as are there's so many other forms of wearable technologies and technologies that become part of us. Clothing, cars, a smart car is an example of a technology, because you see somebody in a parking lot, 2 cars collide, and one of the drivers says, "You hit me." They don't say your car hit me, they say you hit me. And so in many ways we think of the car as part of us, and a car is an example of technology that becomes part of us. There's a very funny joke somebody once said. He said, "Beam me up, Scotty." And then he said, "Now beam up my clothes." That wasn't very funny. And implicit in that joke is the fact that clothing is part of us. We think of clothes as part of us, and the boundary between the environment and the environment is clothing. It's this boundary, and so cars, clothing, and so on are technologies that become an extension of our own mind and body. So we are working on autonomous vehicles as a true extension of the mind and body, and other kinds of technologies that embody humanistic intelligence that arises by having the human being in the feedback loop of the computational process. I will also talk about metavision, the vision of vision, sensing sensors and sensing their capacity to sense. This police radar is an example of a sensor, and what I just showed you is an example of sensing the sensing these sensors and being able to sense. So another form of sensor is a camera. And so another thing that I did a lot of in my childhood was to photograph surveillance cameras. And so here, you can see it up there, I have a surveillance camera. Let me talk about this early wearable computer. So this is what many people regard as the world's first wearable computer. It's been at the Smithsonian Institute, at the National Gallery, at the Museum of Modern Art, various other places. I had this vision of something that we would all carry with us, which was a radio, a television, a music recorder, sound recorder, a computer, a telephone, all in one thing that we would all have with us. And so I built this little prototype back in 1974 in my childhood with a little strap on it to carry it around. And in this box is the idea of a computational system. It's what we would now call a multimedia wearable computer. And so the idea is that we would carry with us all of this sensory capacity and metasensory capacity. On the output side of it, I had display connections here that connected, and here I have an example of a display, an early display with connectors on it, and these connectors plug into that display. This is the early sequential wave and printing machine, very much like the one that I just showed you. And with this, I used to photograph electromagnetic radio waves, sound waves, and more importantly, or certain from a fun point of view, the sensing of sensing itself. So I would often record surveillance cameras with this thing. So I had connected to here one or more light bulbs, a row of light bulbs. At the moment, I have here connected just one light bulb, and there is a sensitivity adjustment. It's picking up radio signals, and here I've got antenna terminals on the back. It's picking up television signals and amplifying them from a rabbit ears antenna. And I've got a bias adjustment here. And when I take that and bring it near a surveillance camera, so when I bring it up in field of view of a surveillance camera, what happens is it gets brighter than it does when it's not in field of view of the camera, so that you can see it's picking up the metaveillance flux from the surveillance camera and amplifying that and feeding it back. So what I've got is I've got a feedback loop, and it allows us to see and understand the valence flux of the camera, so that it creates a record, if you will, of what the camera's capacity to sense. And if I cast a shadow with my hand upon the ceiling, let's say, you can see the shadow of my hand. When that shadow passes over the camera, the lamp goes less bright because it's not feeding back. So this is, and then when the hand passes, the light goes bright again. So you can see, we call this a valence shadow. And so you can see that we can pick up and we can swim out the valence flux of that camera up to a certain point. And when we get a certain distance away, it doesn't pick it up anymore. Let me go wide so you can see that. A certain distance away from that camera. Now it doesn't pick up anymore because I'm too far away. And what I can do is I can put a little bit more bias on that. It's in frame right now, the camera, so it should be glowing bright. If I give it just a little more bias, it'll kick in. and pick it up again. But then the contrast ratio is not as good. So one of the things that, I experiment with different kinds of light bulbs and different lamps. And so I built a slightly more powerful amplifier. With a slightly larger bulb, and I'd sometimes use a 1.5 kilowatt light bulb. A little bit of bias on that bulb. And now I'm able to create a higher contrast image with a slightly larger bulb. So this was one of my favorite childhood hobbies, was going around photographing surveillance cameras and their capacity to see. So as the lamp comes into view of the camera, it picks up its valence flux, and again we see the same phenomenon, valence shadow. As I cast a valence shadow upon it, it falls dim, and when the valence shadow passes away from the camera, it goes bright again. And so this is a light bulb in a mogul base, slightly larger base than standard bulb socket. And this is a grip here. After a while the lamp heats up a little bit, so I put this grip here so I could hold on to it from further back, and thus be able to capture and understand and display metavalence valence flux. And with a row of electric lights, we had this notion of metaveillance or metavision, for which we founded a company. We raised 75 million US and started a company called Metavision around these ideas, and it's kind of an augmented reality overlay. I have here some pictures from my childhood of a surveillance camera captured with this array of electric lights. Let me just adjust here and bring that into view. Just on the back of the door here, I'll open the door a little bit so that we can see it straight on.